Everyone, good afternoon.
Good afternoon, doctor.
Hi. Okay, so I think let's see how many people now. Okay, 29. Maybe we'll just start. Okay, don't forget to send your attendance.
Uh, Doctor attendance is not.
No? Okay, let me have a look.
Yeah, I can't. No.
It's lecture today, right? Okay, try again, see. Should be okay, right?
Yes.
Yeah? Okay, good.
Yeah, it works.
Okay, good. Okay, let me share my screen.
Yes, it works.
Yeah, okay, right, good. Okay, can you see my screen? Yes, no?
Yes.
Okay, done.
Yes.
All right, okay. So this is going to be our last lecture. I think I made a mistake. I mentioned it was going to be a topic on decision making, but it's actually problem solving and reasoning. So, yeah. So it's also a topic that you can refer when you make your assignment or answer your final exam later. Okay. So, all right, first of all, let's look at this because it's on problem solving, right? So today's lecture will be a lot on solving problems. So we'll see how good we are when it comes to solving problems. Right, okay, so if you look at this figure, it says the length of the radius is r, and now we're looking for the length of x. Yeah, what kind of answers can you give me? What do you think x is?
It is also the radius. It is also the radius.
X is also the radius. Okay.
Yeah.
Any other answer? Can we use Pythagoras? Was it Pythagoras? Theorem Pythagoras, right?
Yeah. Yeah.
Yeah.
Yeah. Yeah.
So what would be the formula if we were to use Pythagoras? Come on, your maths is supposed to be better than mine. Is it even possible? Maybe this should be your final exam question, right? Everybody will like, okay, how do I solve this one? Right, okay, so we basically only got one answer. Come on, guys. What other answers can we get for this problem?
Yeah. Yes. Yeah. It's R. X is R.
Okay, just that. Okay. All right, no other answer.
E.
Yeah,
Yeah.
it is the
X is
rectangle.
R.
Because if you see the other diagonal, opposite
At the
X
diagonal, it's
will
a
be the
radius.
radius.
Uh-huh.
Yeah, so X is the radius, I guess.
X is the radius. Okay, all right, okay. So that's basically one solution. I don't know whether or not everybody can see that, but yeah, so we'll probably come back to this later. Okay, that is one answer. Okay, so let's move on. Basically, yes, we started off with trying to solve a problem. Clearly, this is what we're going to be learning today. How well can we solve problems depends on how the problem is actually being presented in our minds. We'll see that there are several ways of how we can solve problems. One of the keywords that helps us to solve a problem is called insight. So we talked a little bit about insight during tutorial this week. So we'll dive deeper and look at the definition of insight and how that helps us to solve problems later. And also look at the difference between experts, how experts in a field differ to another person who's non-expert when it comes to solving problems. And then we'll also look at a little bit on reasoning, how whether or not we reason logically, and whether or not this can actually lead to error at some point. Yeah, and then what it needs to actually help us to make decisions. So these are just a few learning outcomes that we expect to reach by the end of this course. Also the list of topics. Okay. Okay, so depending on how you read that can sound quite how do I put this? Yeah, you can have different emotions, right? Yeah. So what kind of problems do you all experience or do you have? I'm sure all of us have like lots of problems, right? So name a few. At least what sort of problems do you experience today or yesterday or throughout this semester or maybe throughout this pandemic era?
Okay, this is a situation where when it being asked the question, I can't think of an answer.
Which is also a problem, right?
Yes.
Because it feels like, okay, well, what should I give this, an accurate answer, or could I be a bit more like, flexible with my answer? But, maybe, what scope of answer should I give? So that also can cause problems, right? And a little bit maybe anxiety. Yeah, so that's why maybe in exams, a lot of students find it difficult to solve even the simplest problem. Yeah. It's really funny. So yeah, I mean, this is basically just example. You can list him a lot of other problems, but finishing assignment on time, trying to solve math problems, dealing with a relationship, choosing a career after you finish university. These are just different types of problems, but there's different levels of intensity to every problem as well. And this one can also fall into two separate categories, as we will see. So this is just a few examples, and problems again can be quite subjective from one person to another person, right? So what can be a problem for one person may not be a problem at all for another person, right? So yeah, and that brings us to the definition of what problem is. So yeah, by definition, it means that you need to get to some kind of goal. Okay, you have, let's say, a state where you are now, and you have a goal, but there is an obstacle in between that hinders you from reaching this state. Okay, so like just now I asked, what is a problem? What is your problem? What kind of experience, what kind of examples of problems do you have? And you find that, okay, so how should I answer this? What kind of what is the answer should I give? So that alone at least triggers an obstacle for you to reach a goal from your current state. Okay, and of course, different problems will give you different levels of obstacles, and sometimes you don't even have an immediate solution when trying to solve a specific problem. And that is why we have two categories of problems, and one is called well-defined, another one is ill-defined. A well-defined problem is when you know there is a problem, such as finishing assignment or solving math problem, you know that if you put effort, if you know what you kind of know what to do, so you know that eventually you will come to a solution, you will eventually reach your goal. Okay, so this is well defined because it's like there's a rule to solve this problem. But some problems, like, you know, dealing with relationship, you know, sometimes you are in a very toxic relationship, maybe trying to choose what to do after you finish university, or sometimes deciding what to eat. I always have that problem. You know, as much as you have so much options, especially on Grab food, right? You can just, like, you don't have to spend too much time, but sometimes, like, you know, I'll be spending probably 15 minutes, 20 minutes deciding what to eat. Have you at some point experienced that? Anyone?
Yeah, every day I don't know what to eat.
Every day don't know what to eat, right?
Yeah.
Yeah, correct. Yeah, even, like, you know, for housewives, you know, thinking about what to cook also can be like headache, you know, because then you cook everything and the same thing every day also a problem. You don't cook also problem, and, you know, not knowing what to eat also, oh God, headache. So that's true. And another problem, I think another example of this ill-defined problem is if you want to watch maybe a TV show on Netflix, right? Spending a lot of time looking for that series you want to watch, not actually deciding which one. So that's just maybe, you know, eventually you will decide. But this is basically just an example of some of these problems. And ill-defined is when you don't necessarily have a correct answer. Okay, and often, as what's stated here, is unclear. So there's no right or wrong. Whereas when you have a well-defined problem, then often you will basically have, like, you know, a kind of like a fixed solution. So whether you do A or you do B, if you don't do B, for example, like, you know, if you want to score well in a subject, okay, it's either you study or you don't study. If you don't study, then it's likely that you cannot score and therefore have to repeat that subject again, right? But if you study, it is likely that you will at least pass. Okay, so it's clear, right? So these are just, like, you know, two different types of problems. And what we want to look at now is the approach we have to solve these well-defined problems, right? So the first is called Gestalt approach, and another one is information processing approach. So we will first look at this Gestalt approach. So we have learned about Gestalt principle. Do you know the law of, what's it called? Law of, cannot remember now, is it organization? So you have things like proximity, similarity, what else? Good figure ground, another name. Yeah, a few more, right? So I remember we talked about this in the first few lectures. So the same thing, to some extent, we can use to solve problems, and that is one of the reasons, one of the solutions that can be helpful that can be helpful to some people. So you've got this Gestalt approach where people will represent the problem in slightly a different way compared to the conventional approach. Another one is it involves a lot of restructuring and reorganization. So it uses this law of perception organization, the one that I mentioned. So remember when we were looking at this circle problem just now, I know we could solve it using math formula, right? I was talking about theorem Pythagoras, right? And then there's also another way of restructuring that information. So that's why some of you managed to think of X is equivalent to R, because you were probably looking from this point of view, because you know that this is a center point. And if this circle is actually been divided into this quadrant, and whatever that moves from the center point to all of these different angles is considered the diameter. And if we know that the diameter over here is what is it, R, therefore X is equivalent to R, because you know that this is a rectangle. Is it a rectangle? Yeah, a rectangle. Because you know that rectangle over here and over here will be the same. The length over here, the sides here and here will be the same. And therefore, what you have for X will be equivalent to what you have for R over here. So this is how a representation of this problem can be changed and will help you to solve mostly a well-defined problem using this Gestalt approach. But having to say that, not all problems can be solved using this approach. You know, it takes these two principles, at least the reorganization bit. So sometimes a problem, and this sort of problem is actually shown a lot in IQ tests. You know, when we are asked to find, okay, you're given like some examples. There's one example here, another example here, and you're supposed to estimate what is how should the following figure look like based on a progression of a few figures before that. I think you know what I mean. So you see this a lot in IQ tests, and this requires us to use this restructuring or Gestalt approach. Okay, so I hope all of you can see. If you can't, then yeah, and then most likely you're not. Well, you're probably more what is it? Inclined to solve this problem using this math formula. Yeah. Okay, so yes. So another thing that I want to get onto is basically once you solve this problem, right? For those of you who initially came to this solution, you realize, oh yeah, that's that solution. But I'm not sure if any one of you didn't manage to look for this solution, and only now as we discuss about this and start to think about this, and you'll be like, oh yeah, huh? Oh yeah, oh yes, you know, I'm sure we've gone through that stage, right? If it doesn't happen to you, you might want to do this to any one of your friends or family members and see whether or not, if they cannot identify R is equivalent to X, and when you explain to them, you'll be like, oh yeah, that makes sense, right? The point when they reach to that, oh yeah, that makes sense, is what we call insight, okay? And this is basically a sudden realization of a problem solution. Right, so, and of course it is very much associated to being able to see the structure. Like here, you have R over here, and then you know that this R and this X are basically of the same length. Okay, so that is basically the point that requires you to reorganize this problem in this sense if you don't use this formula approach. The thing about insight is, yeah, often it comes with this sudden aha experience. What we say, oh yeah, I remember now. Oh yeah, now that makes sense, right? And I think it happens to one of the. There was a very well-known story. I think it was
The Eureka.
yeah, the Eureka one. Is it what's the name of this
Archimedes.
Yes, Archimedes, right? Yeah. So what happened was, I think he was taking a bath, right? So it was like, was it in a jacuzzi or in a pool or something? And then the moment he kind of like got himself into, like, immerse himself, and then the water starts pouring out, and he said, oh yeah, there must be something here. So, and then he then started to do more and realized that the amount of weight that you put is the same as the amount of water that comes out, something like that, right? So yeah, so that is basically an aha experience, and that is the point where this person actually reached insights. So what's interesting about insights is the solution actually comes to you suddenly. So it's not like something that eventually builds up. Okay, and if for the later part, this is called non-insight. So this is actually proven by these experiments where participants were asked to evaluate how close they are when it comes to solving a problem, a specific problem. So they were given insights problem and non-insight problem. So an insight problem is, I think it was can't remember. Yeah. Okay. So we'll look at these insight problems in a while. So in this approach, answers appears suddenly, and it was found that people were not good when it comes to predicting how close they are when they are close to reaching a solution. But if it is an non-insight problem, okay, it involves a more methodical process. So you have a method, you have a steps. So things like, let's say, a math problem. Okay, so let's say you're given some sort of formula, right? X squared plus 3a equals to maybe 10. Okay, and you have to find given X, you have to find what A is, or given A, you have to find X. So it's easy for you to replace all of these values, substitute and all of these, and do all of this math, copy calculation and reach a solution. So this is a non-insight problem. So you have the knowledge and you know what to do step by step. Okay. So this experiment was done, and in the procedure or the task, participants were asked to rate the warmth of their judgment every 15 seconds at a scale of 1 to 7. So 1 is very far from the solution, so it's cold, and 7, the closer they feel when they come to the solution, their judgment will be more closer to hot, right? So that is the idea. Okay, so 1 is far from solution, 7 is close to solution. And this is basically an example of an insight problem. So it says over here, triangle shown below points to the top of the page. Now, you have to tell me how you can move 3 circles to get the triangle to point to the bottom of the page. Now, can you do that? Can you tell me which point we have to move to get the triangle to point to the bottom of the page from what we have over here? So let's say I name this one 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we've got 10 points. Which points do we have to move? Do you have an idea?
I have an idea. It's 1, 7, and 10.
1, 7, and 10. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's 1, 7, and 10. So 1 move to where?
1 move to the bottom.
Here.
And then, yeah. And then the 7 and 10 just move up.
Which row? Row 1?
To the row 2.
Second row, yeah.
Here and here. Right, okay. So there you go. Well done. So that is basically a solution. So if you see here, this one move here, this one move here, and what you have over here, so this one come to here. So eventually you will have this bit, right? Yes. So for those of you who could come up with this, it's quite quick for you. But for those who did not manage to come out with this solution, and the moment when you look at this, you'll be like, oh yeah, okay, it's that easy. Because some of us might be thinking, right, okay, maybe you have to bring here, you have to rearrange all of these, and that requires more than 3 dots. So this is one example of how quick a solution can come, because it's basically just instantly. Right, so this is an example of insight problem. So well done. Now, so another example of a non-insight problem is the algebra problem. When I give an example earlier on, let's say you have to solve x, and let's say there's some calculation over here, like like 15 to the power of x equals to 10 plus 25a or something like that. Let's say this one is not complete, but let's just assume that's the idea. Okay, so we know what algebra problems or math problems looks like, and often there is a method to solve those step-by-step process. And it was found that when people were doing these sort of problems, if it's algebra, it's here. People could tell how close they are, how warm they are. So this is more like, there is a clear progression, one step by step. As we solve this problem, we can evaluate that, okay, I'm coming close to a solution, so I know, like, now I am, like, level 3, I cannot get the idea. Oh, now I know I have to bring this to the left, to the right side, and eventually it's quite smooth over here. But if you look here for insight problem, a lot of the time we'll be like, I don't know, I cannot see it. It's like, how can you all solve this problem? I just couldn't find the solution. And then, like, you start to get like a hint, and it's basically just suddenly you got a solution, right? So you could really feel, if you manage to do that problem just now, you could feel that, the solution comes to you almost instantly. So this is a problem that has been proven that insights problem tend to happen instantly. That the answer appears suddenly or instantly compared to non-insights problem. Yeah, so whenever now that you understand such things exist, so you are better able to describe your ability to solve a problem, like suddenly, like when you are in let's say in a group, and you have to problem solve a specific problem, and then somebody say, oh yeah, I have an idea, let's do this, let's do that. That's because they're actually going through insights, and it's good because it actually creates boosts out the creativity thinking. All right, okay, so that is that. So now let's move on to the next part. So we know that solving a problem requires us to move from a goal to from a state to a goal. Often we will have like issues, right? Called obstacles. So we have different types of obstacles, and one of the common thing that have been discussed in the area of problem solving is called fixation, or and this is when, let's say, have you been asked or been in a situation where you were given this happens a lot, I think in what is it, in TV shows, right? In I've seen this when people are given, let's say, an item, a tool, let's say maybe they get a badminton racket, for example, and you have to think of its usage apart from its standard use. You know what a badminton racket is supposed to be for, but you have to be creative enough to come and think of something of a different use using this badminton racket, right? And often it's quite difficult, right, to do that. You know, some people are so creative and they'll be very quick coming up with this. Oh, we can do this, we can do that. You can do like many things. Let's say you're given a round figure and you just get, okay, it's a ball, you know, it's a moon, it can be many things, right? But when we come to, you know, where we get stuck, right, trying to think of all of these different usage, right? This is what we call fixation, because we always tend to think or focus on a specific characteristics or specific use of a product, of an item. So, for example, if you look at this one, what do you think it is commonly used for? A flash bulb, right?
It's usually used to illuminate a room.
Yeah, that's the common use. Yeah. Any other thing? If I were to ask you, what else can you use with this item, with this object, with this flash bulb? What would you tell me?
A single-use lighter. If you put too much electricity in it, if you supply it with enough excess electricity, it'll burn. So a single-use lighter.
Okay, all right, okay, all right, okay. Still, it's still along the line of it's like, you know, a source that provides light, correct? More or less. Yeah, okay. If I were to ask you, yeah, what else? If it's not used for light bulb, light bulb. Yeah, go on.
It could be used as a tool to see if a circuit is complete or not. Maybe.
Right. Yeah. Of course. Yeah, we can use that one because, you know, if a circuit is you know, working or not, you can see whether, you know, I'm sure if you have taken, was it physics at some point, maybe during high school or maybe primary school. Can't remember if I learned this in primary school or high school. And then yeah, you can test whether or not a circuit is actually working because then the lights were, but still along the line of light bulb. If it's because, you know, it's giving light, so when you'll be thinking, oh my god, it's so difficult to think of something, to think of its function that is not its original function. So this is a problem called functional fixedness. Okay, so it's because we are trained, we are so fixed to restrict the use of an object to its, you know, standard functions. But of course, if you look at other things, you know, it may not be common, you know, and there's a lot that we can debate, especially this one, but this bit is doable. We have seen something like this somewhere, right? Maybe this doesn't make sense, I would say, but not to say that it's not done. It's not like we cannot use this design. I think I have also seen a water bottle that has this shape. Have you guys seen somewhere? Yes, no?
Don't think so.
I don't think so. Okay, I think I have seen a water bottle of a shape of this light bulb, but probably not all this filament stuff. But you know, this type I have seen. You probably want to Google. Because I got it as a gift from some kenduri kawin wedding gift, I think. Yeah. So yeah, so this is basically one of the issues that we always come across to think of, usage of a product. And now we're going to see how prevalent this can be. Okay, so we look at this. Now, you are in a room with this corkboard on the wall. You're given some candles, matches in a matchbox, some thumbtacks, and your task is to mount the candle on the board so that it will burn without dripping the wax on the floor. Now, you're going to have to give me a solution of how we can best do this. Can you think of one? Anyone with just by using what you have within your own brain power, can you be so creative to think about this solution? Any ideas from anyone? Come on.
Use some thumbtacks to like surround the top part of the candle so that it would like accumulate inside while it's burned.
Top.
Yeah,
Okay. Okay. Okay.
Wait,
and
no.
then?
No, never mind. That doesn't work.
Okay. All right. A different solution, maybe. Come on. I'm sure you guys are more creative than that. You can do it.
Opening up the box into
You have to open the box. All right.
Oh,
make it into a platform, and then you put the candle on top of the cardboard box, and then like that. So it will be it will be a 6-sided cardboard box, open up flat on the floor, and then you put a candle on it. Then you put the thumbtacks, acting like the feet for the candle.
A feet for the candle. Wow.
Yeah.
like how you have a rocket, and the rocket is like trying to
trying to point upwards, with and there's a leg on the bottom. Yeah, kind of like that. Yeah.
Something like that.
Yeah.
Good, right? Okay, but what you're doing over here is you have to put on the floor, right?
Oh.
Because
this is, I guess, the builder from his idea. Like, it says here, mount a candle on the corkboard. Does it specifically say that the candle must be attached to the corkboard?
Well, it doesn't say, but the task is basically to mount a candle.
Yeah.
So mounting a candle on a corkboard, it's quite flexible, right? So long that you can, it's somewhere kind of like floating.
Okay, so a possible idea would be probably to use the matchbox, attach the matchbox to the corkboard, and then attach the candle to the matchbox. Then if you while you burn it, the wax will melt into the matchbox instead of the floor. So it is technically mounted to the corkboard, and the wax won't drip to the floor.
Absolutely, well done. So that is the answer, more or less. So your idea probably is basically it's the other way around, right? So it could be this way, which is, while it's a little bit more stable. Another way, one of the common solutions students always give is basically you, instead of putting the candle on top like this, the cardboard itself is basically sort of like the other way around. So this actually goes inside here, and you mount it this side from Yeah, if you know what I mean. So yeah, and that is a little bit less stable, I think. This is probably a little bit more stable. I mean, of course, depending on how large your candle is. Maybe over here it looks really large and probably not as you know, wouldn't be equivalent to the size of this matchbox. But assuming that you have those candles, like, you know, the birthday, like the pink and white candles where you get with birthday cakes, you know what I mean? That is possible, I think, right? Yeah, so that's why it's interesting to see how, you know, how many cycles of iterations we need to think to reach the solution. And that's why a lot of the time, solving a problem in a team is always a good thing, because you can get one person can come up with an idea, but that idea normally gets to be built up or improved from one person to another person, compared if you were to sit down and try to think this yourself without Googling. Of course, if you rely to Mr. Google, it's like, you know, instantaneously you can get an answer. But if you were to sit in, like, you know, a team of people and have to solve like problems where you don't even have a solution on Google, it can be quite tricky to do this all by yourself. So one tip to take over from here is, you know, working in a team is a good thing, right? Okay, so this is one of the solutions that we can do. And this is actually repeated in different versions of experiments. And one of it is to see how well people can actually solve the problems depending on what is given to the participant. So yeah, so in this this kind of experiment conducted by Dunker showed participants two representations of the items. One is what they call algorithmic, where you provide an empty box to them. Another one is heuristics, when the box is there as a hint to become a container. And people were able to solve the problem more if it's in this form. When the box given to them is empty, then they can think, all right, I can make use of this box because it's empty. But if the thumbtack happened to be like this in a container, all right, which is something like that, the probability of solving that problem reduced by 50%, maybe less than 50% actually. Yeah, about that, maybe about that. So this is basically the, you know, how well a problem can be solved depending on how the problem is actually being posed, right? So yeah, so this is basically one of the things that was done and proven that if what's happening, if this is done, then a lot of people can solve this problem a lot better because they actually take this empty box as an option. Okay. Now, this is another problem. So you've got over here our friend Sebastian. He tries to grab another string. Okay, he's actually at two sides over here. So he cannot grab the second string now, but what he needs to do is he needs to tie these two strings together. So let's try to see what we can do to help Sebastian. So what solutions do we have over here?
There's a pair of scissors.
Again?
There's a pair of scissors on the ground, I think.
Okay. You see scissors, okay, right. What can we do with that?
Cut both strings off and then just tie it up.
Right. So that's easy. Okay, so that's one option to cut it off. Assuming, okay, probably that's not clear. Assuming that you're not allowed to cut the strings, you know, the strings is attached as they are, and you still have to tie them together.
I think one of the solution can be he swing the first string and then rushes to the second string and grab it and then run back to the center and then grab the first string while it swings back.
What if when he swings the string, right? What if it doesn't go as far, or it doesn't come to him quick enough? Maybe there was no air. Maybe the string was basically not moving that fast as expected, as he was running between the two.
Perhaps he can tie the scissors onto the string, but it will be very dangerous.
Dangerous, right? Yeah.
For
okay,
the
but And then what's with the chair then?
Use the chair as an
I-
in-between?
Use the chair as the again?
As an in-between.
In between, like how? Like tie the chair to himself, or tie the chair to tie the strings to the chair.
That.
You guys are so close.
I
So
Take some
close.
take some loose string from his shirt.
For me, what? So yeah.
Just stand on the chair so that the distance can be shortened. Something like that.
Stand on the chair, so distance will be shorter. Okay, and then like which side? Like to the left, to the right? Where should he put? Where should he put the chair now?
Put the chair in the middle of the two strings, and stand on it to be able to. So he should be able to catch the second one, I think.
And then then he hold one and he catch another one.
Yeah.
How about
think-
he's currently holding one string. So he ties that. He uses the chair, stands on it, and then ties that one string's end on the lamp thing.
On the lamp.
Is it possible? Like there's like that one like protruding part on the lamp.
On top there.
Yeah.
No, I don't think that one is like doesn't make sense. Could be too high. I think.
Ask the person who takes the picture to help.
Again?
Ask the person who takes the picture to help.
I cannot hear. Maybe I have to be Yes.
I think he was trying to say to ask the person who takes the picture to help him.
That's very creative. Assuming nobody exists there to take. That's just like us assuming that we're assuming this in our own brains. Yeah. You're so close. You just have to puzzle the pieces of your solution.
I think I have some way. So let's say we get the second string to tie into the chair, so it will be extended to the middle, the second string, and then take the first string, then go to the chair, and then grab the string to tie it up.
Right. Okay. It is likely that the string is not long enough to reach the chair.
Oh.
It looks like it. It looks like the string and the chair is not like opposite. That they don't reach.
Well, since the chair it looks like to be act like extended arm. So first tie the string to the chair. So and then we hold the chair at its leg, so it will be extended. The string will still be pulled while it be tied to the chair, and we hold the chair's feet and then get to the second string.
Oh, lots of acrobatic happening over there, right?
Assuming he can one hand the chair lah.
Okay, that is a little bit complex, I would say. Yeah, well, yeah, depending on whether or not because you mentioned about this tying the string to the what is it to the chair, right? Yeah. Okay, any last ones? All right, it could be. We'll discuss what the solution is right now. But any last ones from anyone?
I still think the scissors must be tied to the scissors first. Maybe the sharp point should be pointed upright, so it won't when it's swinging it won't harm people. Then push harder, then let it swing with higher amplitude. Then we can catch the string. Then we can basically when the string going back, then we can catch the string and tie it together.
All right, well done. Do it as a pendulum, right?
Yeah.
That's right. So what you do is you tie it to the plier to one string to create a pendulum and then switch it with another person's reach. So that is a solution. So what you do is sometimes you may or may not be using all these items needed. So whatever you had, it could be, but it could be basically quite a complex solution. But the idea is you tie this one and you hold one, you tie this one, so you have to swing it very like, okay, you lose, you can let go first, you tie one of these or this one, okay, and you swing. And of course, you know, when it creates a pendulum, you know what a pendulum is, right? So it go very, you know, the further the power is, then the further it will go, and you have enough time to catch the other one, and when it comes back to you, you can actually get one from scissors and then eventually let go of this plier or scissors, and then you can tie. Okay, you may or may not be using this chair. So 60% actually did not manage to solve this problem if they look at all of these as the standard use. Okay, but in a different version of this experiment, as he was explaining to the participants what they needed to do, and if he or she accidentally brushed the string and the string actually moved, and then people actually got the hint, and about 20% to 30%, 40% of people managed to solve this. So that's why, so when you guys were actually, again, doing discussion, coming up with all of these ideas, so you managed to build up your ideas and like get some bits or pieces from the hints given by the previous problem solver. So again, this is one of the reasons that, you know, reaching to this functional fixedness is a very common problem, and it's not as easy to think of a problem. This is when people say think out of the box. You really have to think out of the box, and it's not just like, okay, as easy as how it looks like. Okay, so yeah, so there you go. This is one of the solutions that you can get. Of course, we can go on and on. It can be a debate if we talk about this, but yeah, and these are just two types of problems that Gestalt principle can be used, or Gestalt approach can be used, depending on how we frame the problem. Okay, so yeah, well done and good try. So we have looked at this Gestalt approach. Now we want to look at the next approach, which is what we call information processing approach, and this is based on a searching principle. So based on a more algorithmic procedures. Okay, information processing, and a very common one is this thing called Tower of Hanoi. Okay, I'm sure you have seen this problem. We have done it probably in programming before, and it's been introduced by this Alan Newell and Herbert Simon. These are also computer scientists, if I'm not mistaken. So they identified problems to have different stages, right? So, or different state. The first is what we call initial state, and we know that we want to reach a goal state. So this is your initial state, and eventually you want to do something, process, right? Lots of steps so that you can eventually get this. Okay, and you will have a lot of like rules. You can move this one from one pack to another pack, but maybe a larger one cannot be on a smaller one. Okay, but a smaller one can be on a larger one. That's not a problem. So you have like a series of rules, regulations that you have to follow, and of course, in between, you will have a lot of intermediate states. This also makes it sometimes less, how do I put this? Less obvious for some of us to think of a solution, especially programming problems, right? You're given, let's say, a programming problem, and then you have to come up with a solution for this problem. You can just read this problem statement. Some people can get like a series of codes. Some people struggle. So that's because of where we are, you know, what operations we know, what rules apply, what rules cannot be applied, and you know how well we actually represent all these intermediate states. That's what we see over here. So you know, the same goal can be solved using like different approaches. So you can start to put your the very first disk on, let's say, on this second pack, on this third pack. So depending on where you move or where you put, that will also lead you to different steps or different intermediate states, but that doesn't mean that, you know, if you go this path you cannot come to this solution. Not necessarily. You can, but maybe it will take a longer path or a shorter path. So that's why when somebody is asked to solve a problem, there is no single approach or there's no single way of solving a problem. If I ask you, how do I get to UM from, let's say, the University LRT station, right? Okay, so, you know, if you're used to this, then you can already imagine, okay, you can take a bus, or if you drive, or if you ride a bike, go this route, take this route, go into the KL gate, or you know, go into KL gate will be probably the shortest. But that's not the only option. You can also go to UM, but use the PJ gate instead. Okay, if other people say, oh no, I want to use the Damansara gate instead. Okay, it's not like you can't, but it's a longer path, right? So this is an approach that uses this process. But of course, the longer, then you will use more resources in terms of time, in terms of processing power, in terms of capacity, many things. Okay, so that's why we always try to solve problems in the shortest time, most efficient approach possible. Okay, what we want to look at now is how and the importance of how a problem is basically stated actually determines how well we can solve the problem as well. And first of all is the program of the problem difficulty. Now you have solved this the Tower of Hanoi, right? So you know that, okay, you have certain rules that you can apply, and you have one state to another state. So you have the initial state and you want this goal state. So this is a variation of that problem called acrobat problem. So you have all these acrobats of different sizes. So this is maybe the smallest, this is like medium, this is a little bit like, you know, large. So you have this initial state and this is the goal state. So you can solve this problem using this series of rules. So then let's say it says over here that only one acrobat may jump at a time. So okay, you understand. And then you have whenever two acrobats are on the same flagpole, one must be standing on the shoulders of another. Okay, and it says that the person standing on the other one is a bigger one cannot stand on a smaller acrobat. Okay, so you cannot have this person standing on this person or this person standing on this person. Okay, so that's the idea. And an acrobat may not jump when somebody is standing on his or her shoulder. So let's say somebody is already this person is standing on here, so they cannot jump, only the other person can jump. So you know that now that you understand how this Tower of Hanoi works, these rules is somewhat similar, and you can eventually solve this problem, okay, using that. So the results basically took, participants actually took about 5 or 6 minutes to solve this problem, because they can apply the previous problem, Tower of Hanoi, to this problem. So it's relatively quick, I would say, because it's more or less in principle, right? But if, let's say, the problem becomes reverse, which means that the regulation is actually changed at this rule 4. It says over here, let's say if you change the rule and say a bigger acrobat may stand on the shoulder of a smaller acrobat, let's say, right? It says that change the state, smaller acrobat, smaller acrobat could not stand on a larger one, the opposite, yeah. So the reverse is the same. And it actually takes longer, about 10 minutes to solve this problem. Why? Because you now have to consider different rules, and therefore your state becomes longer because it is less traditional, it's less common for you. So you have to think of more intermediate steps in between. So this is a problem when, as the problem becomes more difficult for an individual, okay, of course, depending on their previous knowledge, depending on their experience, depending on the rules that's applied, depending on the understanding of the rules, many things actually, their ability to solve a problem can become, can take more time because it's considered more difficult for them, okay? So this is again on that. And this is another problem. So let's look at this and see whether or not we can solve this. Okay, so you have a checkerboard over here, just like, is it something like chess? Okay, so you have, so this checkerboard consists of 64 squares, and these 64 squares can be completely covered by placing 32 dominoes. You know a domino square? Okay, so on the board, so each domino covers 2 squares, right? Like this. So now, if we were to eliminate 2 corners of this checkerboard, let's say you eliminate this one and you eliminate this bit, can we cover the remaining squares with just 31 dominoes? Tell me if it's a yes or no, and tell me why.
No, using
No.
the pigeonhole principle.
You're using pigeonhole principle. Why so? What does this pigeonhole principle says?
It says that like if you, I don't know how to explain it properly. Like that means that if you have a specific number of boxes, you can't, and you have more items than a number of boxes, then one of those boxes must contain more than one item. So in this case, the pigeonhole principle will work because the
Well, I think I can try to explain. I agree with Stanley's answer using the pigeonhole principle, because one domino, if you see, it will like occupy one odd and even space, and if we start to count from the left piece, it would be 1, and if we count left to right and then alternating to the top, the last one would be 64, and then one is even and another one is odd. So yeah, it cannot fit.
Okay, so the answer is no.
No.
No. Right, okay. Yeah, okay. Right. Any other answer? Thank you. Right, any other answer? Anyone? Any yes here? No?
No, I don't think so.
No, so everybody agrees with that. So it's a no, eh?
Yeah.
So okay, right, okay. So yeah, it's true. Yeah. So basically, if you look at here, of course, if you yeah, so our friend's explanation actually applies it really well. So you cannot move one of these because otherwise a domino actually comes as a pair, right? So you cannot like remove one because the other one will also be removed. So yeah, it's not possible to just remove one part of a domino piece. So that's basically you cannot make up just 31 dominoes. So let's see how that can be further explained. So this was actually shown given to the participants to solve this problem in different variations again. Okay, so one is basically when something is completely blank. Another one when you have this black pink color combination, and another one black pink again. So famous, right? Blackpink as words, right? And another one, another representation such as bread and butter. So we know that dominoes uses 2 squares, right? And it comes as a pair, right? You know, it is unlikely for us to break them apart because, you know, a piece is basically 2 squares. And assuming, let's say, and it covers 2 different squares. If you put a domino, let's say over here, one will take one color, another one will take a different color. And if you remove one here, then you won't have enough color because the solution is you have 31 pink and 31 black, right? But if you remove 2 pinks, then it wouldn't be enough because they come as a pair. So it's as if you can put this representation in this format or use this sort of like logic, then it makes sense, right? And it is so the participants' performance actually differs depending on how the problem is actually shown to them. So if it was shown, let's say bread and butter, now every bread and butter is a pair. Now if I remove 2 butters or 2 breads, can I make up enough combination of this bread and butter? Of course, clearly it's like instantly we can say no, okay, it's not enough because, you know, they need to be a pair. So it's very different. So it's very easy to solve. And of course, the same applies to you if you use like, you know, the black pink combination as text as well. Doesn't matter this one or this one, but this one makes more sense because of the semantic. And well, this one and this one also more or less the same, only different representation. This is color and this is text. Maybe color makes it better. But I wouldn't argue because I think text also makes more or less the same. You can also represent this one as icon. You have a bread icon here, you have a butter icon here. So maybe it gives the same result. It'd be interesting if this one is replicated. But What is most difficult is when you have all this as a blank piece, and when you present this question and ask people to solve, maybe people will have a hard time to come with a solution, right? So this is just a few examples of how these problems can use logic, and reaching to this solution can also be different depending on, again, the representation. And again, it uses a few steps which is applicable at the level of this information processing approach. Okay. Okay. And that is that. Done with all these different variations of problems. What we want to look at now is at how experts solve problems. I think we look at this at some point. There was a topic on I think expertise when we had experts playing chess, if I'm not mistaken. So a little bit more detail about this. We know that to make up an expert, someone actually devote a large time learning a specific field. Okay, they are normally called an expert because they know a lot about a specific field. And let's say if you know, like gamers, right? I think there's this esports. You guys probably play games, may know like a few names of people who are like considered experts in playing games. That's because they spend a lot of time in the field, okay? And of course they practice a lot, and they learn a lot during that process. And they become acknowledged as being extremely knowledgeable because they know very, very well in their particular field. So if gaming is their field, they know very, very good. So they can maneuver probably very, very quickly. They can think of solution or strategies, or they probably have very good problem solving skills. Depending on what games they play. This is just one domain, but if you are expert in, let's say, physics or chemistry or biology or medicine or even computer science, then you will be an expert in your specific field. It's very, very rare these days to get experts in multiple fields, unless if you have devoted your life learning different domains. Like, scholars those days, they know about medicine, they know about physics, they know about social science studies, they know about many things. But that's because of how they probably, probably it's their mindset. Maybe because they were having a lot of difficulties at that time that they struggle to know many things. Could be that. But now, these days, I think we're often to be an expert in a very specific domain. And when someone is considered an expert, most of the time they are able to solve the problem a lot faster with a higher success rate compared to novices. Let me ask you a question, right? Do you think experts are smarter than novices? Yes, no? Anyone?
In their area of expertise, yes, I would say so.
Yeah, probably because they have knowledge. Not just that, they may have the same amount of knowledge when they start to learn something, but because they are so good at, even probably with them not knowing consciously, mentally, the information gets to be organized in a structured manner. So that's why they're considered more and less smarter. But there have been studies where they learn, expert and novices learn a new thing, like, even within the same domain, like, at the same time. But these experts tend to be showing better performance because of their ability to connect their knowledge with existing knowledge better. So they're also, and because of that as well, they become better doing reasoning in general, not just their own area, but in a greater domain as well. And do they approach problems in a different way? It is likely, yeah, because of their of how knowledge gets structured in their minds, because they can actually activate other knowledge, right? And because the neurons in your brains get activated very, very quickly, and they're connected in a, I would say, in a more condensed way. So that's why they're able to solve problems in in a better way. So that's why if you speak to someone who is an expert in the field, you'll find that they'll be very quick when it comes to trying to think about alternative solutions. So these are just some characteristics of an expert. Clearly, they possess more knowledge. This can be seen in one of the in the chess experiment that we look in previous topics. So yeah, experts' knowledge is also organized differently. They're more structured. Okay, novice is because they often look at things on the surface. So when you try to become an expert in a specific field, try to look deeper. Try not to just memorize, okay, or do repetitive or maintenance rehearsal, because that will not help to develop the neurons between other neurons in your brain. So experts do based on deep structure, and this is where you have all of this elaborative rehearsal coming in, because you tend to be, of course it's not easy, but if you train yourself to understand the deeper structure, the deeper understanding of why something happens, what is the relation of one aspect to another aspect, then you're sort of like helping your brain to develop a more structured organization. And once you develop that information stays in your brain longer. So and they also spend more time analyzing the problem. So they can have a slow start. When, let's say, they're giving a problem, right? They may take time to understand the problem, but once they understood, they'll be very quick when it comes to solving it. Okay, because during understanding, they're trying to evaluate, okay, which part of other knowledge or concept needs to be activated in my brain now. An expert are often know better when it comes to problems outside their field. So let's say if you're good in agriculture, for example, and if you've been tested on computer science, so maybe you don't have that knowledge in computer science. So let's say like someone who is in political science, wouldn't have the same knowledge as someone who is a chemist, or like, a novice political science person. So that's why the range of information or domain knowledge can be different from one person to another person. All right, so that is all we have for problem solving, and now we're just going to be looking at reasoning. I think reasoning is a relatively short topic. Before we move on, any questions on problem solving?
No, doctor.
No? Okay. So do you want to take a break? Shall we take a 5 minutes break?
Okay.
Yeah, okay, 5 minutes, yeah, then we'll come back.
Okay, doctor.
All right, shall we continue?
Yes.
Yes.
Okay, hang on. Let me see, how do I do this? Hang on. Okay, so the next topic is on reasoning. Okay, we know that we have two types of reasoning. So it's basically a process for us to reach a conclusion. That's basically your reason. You, like if I ask you, okay, do you choose A or B? And then you have to tell your reasons for choosing A and B. So that's part of reasoning. Because you have to think about why you choose certain things, right? And it involves a lot of logic over here. So one is called deductive, another one inductive. So this is involving a sequence of statements called syllogism. Okay, and another one is inductive, where you arrive at a conclusion about what evidence is probably true based on evidence. So we learned about this, I think, already in critical thinking and communication skills, if I'm not mistaken. So yeah, so for you can still remember. So it's about how people reason from premise, and for inductive it's about how people reason from evidence. So an example of deductive reasoning is, let's say C grade is required to graduate from UM. Okay, and Amanda graduated from UM, therefore Amanda had at least a C grade. Okay, so that's like, you know, all these different types of combination of premise and conclusion that we have used. But for inductive, it's more like evidence, right? Maybe we reach a conclusion because of all of this series of evidence we gain. For example, Richard attended UM for 4 years. He graduated and became CEO for Maybank. So we cannot say for sure whether or not he graduated. Okay. We can't say he definitely graduated. He just said that he attended UM for 4 years. He graduated. So we're not sure whether that 4 years, whether or not he dropped out from UM and then he continued and studied somewhere else. And not sure whether the degree or, you know, master's or PhD he gained from UM actually led him to this CEO post. It could be that his father owns the bank and made him the CEO, right? So it could be so many a reason that you don't necessarily have to follow certain rules compared to this deductive approach, where you have this premise and conclusion. So at inductive first, where we have this premise based on observation of one or specific case. So let's see. So this is our observation, okay, and this is our conclusion. And we see that all crows, I've seen here in Malaysia are black. So when I visited my brother in England, the crows I saw were black too, were all black. So I think it's a pretty good bet to say that this type of animal, crows, are all black, because wherever you go, it doesn't matter whether you're in Malaysia or you're in England or you're in India or wherever you are, you see this animal, this color. Okay, so it's a known conclusion based on your observation. And you can see also based on observation that here in Japan, the sun has risen every morning. The sun is going to rise in Japan tomorrow. So it's clear that, well, this is basically the standard that's going to happen based on everyday observation. This is happening, and tomorrow also will happen to be the same. Okay, so this is based on this inductive reasoning, where we come up, we reach this conclusion based on our experience. Okay, so inductive reasoning. Whereas deductive reasoning requires us to apply some kind of logic, okay? And we have a lot of different types of deductive reasonings, okay? Some of it happens to be in this way, where you see all birds are animals, all animals eat food, therefore all birds eat food. So this is a common principle between this premise and conclusion, and you can change all this information, but it comes from this logical combination of premises and conclusion. We say if all A are B's and all B's are C's, therefore all A's are C's. Okay, so it's that applies. So This is one example. Another one that we can say, like, you can have this two premise of this valid syllogism that are true, and the conclusion must be true. So you say all birds are animals, all animals have 4 legs, all birds have 4 legs. Is it true? I think we have seen birds with, like, say, like 2 legs, right? And most birds have 2 legs. And then if you see, all of the men are tired, some tired people are women, some of the men are women. So it's a bit like, okay, it sounds a bit like confusing over here. So even though you use deductive reasoning, there'll be some issues with this combination of premise and conclusion that can be quite misleading, right? If you use this approach, and you can see that 3 or 4 are still valid in terms of the logic, but the contents are, like, quite arguable. You can say it's incorrect. So you wouldn't say men are women, men are men, women are women, right? And normally birds have 4 legs. What birds have 4 legs? I've never seen any. Yeah. So yeah. Okay. So that's an example. So but it is also useful to help us to come up with conclusions. So let's look at this. If, let's say, we have 2 premises that leads us to this conclusion, if I lend Steve 20 ringgit or 20 ringgit, then I won't get it back. I lend Steve 20 ringgit, therefore I won't get my 20 ringgit back. So it's like, understood. But also, just to prove that these mistakes can happen, let us see this example. Okay, it's this problem where, let's say, you have 4 cards. Okay, so let's read this. So there's a letter on one side of each card and a number on the other side. So this is one side, and if you turn on the other, like the other side, you should have like either a number or a letter. So one side letter, the other side number. So we see a combination. So if there's a number over here, you should see a letter behind. If there's a if there's a letter, there's a number. There's a number, there should be a letter on the back side. Okay, so your task is to indicate the minimum number of cards you need to turn to test the following rule. So we have this rule, and we have to turn X number of cards. Okay, now you tell me how many number of cards we have to turn over to test this rule. So the rule says if there is a vowel on one side, okay, then there is an even number on the other side. There should be an even number on the other side. Okay, so to prove this rule, how many cards would you pick? The minimum number of cards you would pick to satisfy this rule. Can I hear some answers here?
3.
3, okay. 2, okay. 2, right. Okay. If you say 3, which cards would you turn?
I mean, if it's 3, I guess it wouldn't matter. Any 3 combination should work. EK4, K47, E47.
E47, right. Yeah. Okay, all right, okay. And if it's 2, which one would you turn?
Just turn the vowel and the 7, because you want to prove if it's a vowel, then the opposite must be a even number. And the reason you turn 7 is that to make sure that the letter behind the 7 is not a vowel, because if it is a vowel, then it contradicts with the rule.
The rule, right?
Yeah, but you don't need to turn the 4, because even behind the 4 is a consonant. It does not contradict with the rule.
Because it says a vowel, right, on one side. Yes. Yeah. And how about K?
K is not necessary, because it doesn't matter is it a even or odd number, because anyhow it will not contradict with the rule.
Absolutely. So it doesn't say what the rule is. Nothing to do with the rule, because the rule said vowel, right? So that's true. Yes. So yes. So that is basically the solution. The minimum number is 2. You can say that you can turn 3, but any 3, but that's already going to the maximum. So that's actually the correct explanation. But let's see. For those who's still not sure, let's go through and see. So this was actually shown to people. It was actually an experiment. It was shown to people, and the outcome of this experiment said that definitely many people said E has to be turned over, all right, and because you want to see, you want to check, because there's a vowel here on the other side, you want to check whether or not really you have an even number or an odd number. Okay, and okay, so that is basically 50%, and 46% said 4 must be turned over. Okay, if you have 4 over here and then it says that it's incorrect, then it tells that nothing, well, it's incorrect, but it tells nothing if no vowel, because it's nothing to do, well, if there is vowel on one side, then there is an even number of the other side. So because you know that this is like, if there's even number, then it's fine, because you already sort of like, this is already like known, it's like an even number, so it's like a vowel behind. But this one you need to prove whether or not it is true. And 7%, only 4% said that this must be true. So this is basically correct, because it would reveal if the vowel will actually disconfirm the rule. So the idea of what you are trying to do is you want to prove whether or not any one of these will actually falsify the rule. And that's what we want to look at. So in order to falsify, okay, so and this is basically the principle. In order to do that, you only need to turn 2 cards. Okay, which is basically correct, E and 7. Okay, this one doesn't matter because it already stated even number on one side, definitely you will have a vowel on the other side, because this one like because it says if there is a vowel on one side. So this one doesn't really matter because you're actually looking for a vowel in front and not behind. Okay, so there you go. So you have 2 cards, and this is basically the key point to solve this problem is using this principle called falsification. You want to falsify whether or not, okay, if I turn this one, is it true or not that this rule applies? Okay, so yeah, so that is the idea. And this is basically further, then this is basically, if you're still confused, if I turn E, then the result is even, then it confirms. If I turn E, the result is odd, then it falsifies. Okay, so you do the same thing for all of this, and you identify that in order to falsify, you only get 2 of this, which is E and 7. Okay, it may sound a little bit confusing probably in this case, in this type of problem, but if it was actually presented in here, let's see how well you can do this. So you have 4 cards, and each card has an H on one side and the name of the beverage on the other side. Okay, then imagine, let's say you're now a police officer and you want to apply this rule. Okay, if a person is drinking beer, then he or she must be over 19 years old. And then I'm asking you, which of these cards must be turned over to determine whether or not this rule is being followed? You tell me which one of these. Anyone?
I guess beer and 60 years old.
Yeah.
Following that, beer and 60 years old.
Beer and 16 years old. How about soda and 24?
So you don't need to turn soda because it's basically not a beer. And 24, you don't need to turn 24 years old because it is legit for him to drink beers also. So these 2 are not necessary to be turned.
Exactly, because it's like not related, right? So that's why. So in this case, maybe solving that same problem in a different version on different representation is a lot easier compared to the earlier one, because now you know that, okay, I need to kind of like, prove this rule, and which one of these actually disprove this one. So you just need to check for beer and 16 years old, which is true. So these are the 2 solutions that you have to check compared to this one, because this one not related, because you're only checking whether drinking beer, because even if you turn this around, it doesn't really make much difference, because you're only checking if the beverage is actually beer, right? And for this one, it's totally legit to drink because it's over beyond 19 years old and he's 24, so it doesn't apply, right? So you're left with this bit and this bit. So there you go. So this is basically how what we have looked at. This is actually the last slide. So we don't have slides anymore. So what we're actually looking at here is again, doing reasoning can be quite confusing. Okay, but again, it depends on how a problem is being represented. So if this problem is being represented like this, it's a lot easier. But to some, even this one is also easy. But to some, it's like it needs a bit of thinking, right? Like why 3, why 2, or do I have to turn all 4? It also depends on how well we understand the question. And what we have looked in this part is we have 2 types of reasoning. One is deductive, another one is inductive. So inductive comes a lot from experience, observation, whereas this deductive requires us to apply the combination of premise and premises to reach our conclusion, depending on how we design our premise and the first and second premise. However, mind you that we don't necessarily have to, applying this rule doesn't mean that we can accept the outcome if we were to apply the content, just like in this case, because this can be quite misleading. So we have looked at, I think in K2B2, we look at, what are some examples where this can be misleading, and this is also proven in some of these examples, such as this Wilson for cut problem, as well as this beer problem. All right, so that concludes our lecture. Yay, you've well done, everyone, for finishing up to week 12 of lecture. So we won't have a tutorial for this. That's really just for you to know. Doesn't mean that you shouldn't apply. You can apply this one in your final exams if you want. I'll make this one available later. And another thing that I want to discuss with you is class on Tuesday. Because we won't have a tutorial, so I think I will let you have a Tuesday class on your own to finish off your project, because you have to submit your project on the 10th, right?
Yes.
Yeah, okay. So unless if you want to have class, then we will have tutorial, but otherwise I think yeah, I prefer to leave that class for you to finalize your projects. Are we okay with that arrangement?
Yes.
Yeah.
Okay.
All right, good. Okay, so yeah, so we'll meet again on Thursday next week, and on Thursday next week is when I'll discuss your okay. So on the 10th is when I will release your final exam question. So I will describe things with you. So make sure that you come on class on Thursday, and of course you have to submit as well your work on by Thursday, if possible earlier, but Thursday is going to be the last day for your submission. Okay, again, copy your assignments using the assignment feature. Just one submission is enough to represent the entire team, or probably, did I? Yeah, okay, yeah, okay. So only one person submit. Okay, so that one person can be anybody from your team, but you have to identify which team you're from. All right. Okay, any questions from the class?
No, doctor.
No? All right then, no questions. So I'll see you guys on Thursday. Thanks, everyone.
Thank you, doctor.
Okay. Thank you, doctor.
Thanks.
Thank you.